So in this video, I want to go over some of the homework problems, some of the practice homework problems. I'm not actually going over the exact ones. I'm going over similar ones that I think will help you in both the practice homework and then also on the graded homework as well. I went through the problems as I was planning this to sort of see what I think you need to know that people sometimes struggle with. So first, there's some more background I need to show you, going back to roster notation or listing elements of a set. For really long sets, we don't want to list all of the elements because you might have dozens or even hundreds of elements in a set. And so if a pattern continues, what you're going to use or see is an ellipsis, those three dots, to show that it continues. So for example, if set A is considered the set of all letters in the English alphabet, rather than writing all 26 letters, we might instead write it like this. Set A contains the elements A, B, C, D, ... through Z. If set B is the natural numbers between 1 and 100 inclusive, that means we're including both 1 and 100, it might be written like this: 1, 2, 3, 4, comma, ... 99, 100. Sometimes the last two elements of a set will be included there, sometimes just the last element will be. So this should be enough. There should be enough in the problems you see for you to recognize the pattern. Sometimes they might be counting by 2s or 3s or 5s, or there might be some other pattern. So this is a problem that people usually struggle with, and so I want to go over it. And one strategy to solve problems is to solve a simpler problem. And that's the problem solving strategy I would use for this problem. So you're given this example for set Q. Set Q is the numbers 25, 26, 27, ... That means it continues up through 35. What is n of Q? What is the cardinality of set Q? Stop and think about that for a second. And yes, this is a trick question. People get this problem wrong. So let's consider a simpler one. Rather than going from 25 to 35, let's go from 25 just to 28. So first we'll write like the problem is written, but then we only have a few elements. Let's list them out. 25, 26, 27, 28. How many is that? There are 4. N of R is 4. But when people see a problem like this, what they want to do is subtract. They want to take 28 minus 25, which is 3. That's not the answer. We see that. There are 4 elements here. 28 minus 25 does not equal 4. So when we look at our problem here, many people say, oh, 35 minus 25, that's 10. The answer is 10. But we've seen by doing a simpler problem that 10 can't be the answer. So what is n of Q? Well, we know it's not 10, but based on the pattern we saw with our simpler problem, we know that it's that difference plus 1 more. Because when you subtract, basically you are zeroing out the original number, the smaller number you're subtracting. So we want to add that back in. The fact that number exists, not the value of 25. And so n of Q is 11. And here, this is a relatively short list, so we can check it by listing and counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here's another example. Set W equals 135, comma, ... 101. We want to know what is n of W. Notice here we're counting by 2s. So if we were counting by 1s, our answer might be 101. In fact, it would be if we were counting by 1s. So it would be 101 minus 1, that's 100, plus 1, that's 101. But we're counting by 2s. Again, let's look at a simpler problem. Let's say that X was 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21. So list them out, just count them, say, oh, the cardinality of this set is 11. How can we get to 11? Well, we know we're going to look at the last number and the first number. Here we're counting by 2s. So divide that by 2. 21 minus 1 is 20. 20 divided by 2 is 10, but then we're adding back in the number we started with, or we're adding back in that we have a number to start with. So we're going to add 1 to our answer. Same thing here. for n of w, from 1 to 101 counting by 2's. We have 101 minus 1 divided by 2, and then to that difference, to that quotient, add 1. So using PEMDAS, we have parentheses first, 101 minus 1 is 100. We have division second, 100 divided by 2 is 50. And we have addition and subtraction third. 50 plus 1 is 51. And that's our answer. If we were to list by count from 1 to 101 by 2's, we would have 51 numbers there. A set has 1,024 subsets. How many elements were in the original set? To solve a problem like this, we need to think back to our subset formula. Remember, the number of subsets of a set will always be 2 to the n, where n is the number of elements. So in this problem, 2 to the n equals 1,024. Now there's actually an algebraic way we can solve this. We can solve for a variable that's an exponent like this. We don't need to worry about that here. Here we know we're listing powers of 2, and the powers of 2, we just list those by starting with 2 and doubling them each time. 2, 4, 8, 16, 32, 64. I have these memorized because I'm a computer nerd, and I have been since the 80s, and since computer memory works in powers of 2, these are values that I was and remain very familiar with. But even if I weren't a computer nerd, I can just start and double, just multiply by 2 each time. And so I stop when I get to 1,024, and then I count. How many powers of 2 is that? It's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Check with the calculator. 2 to the 10th power is 1,024. And so that meant n equals 10, so there must have been 10 elements in the set. Remember, this is the formula for the number of subsets. If a problem like this, we're asking for the number of, we're giving you proper subsets. Instead of 1,024, they would say, oh, it's 1,023 proper subsets. If it's a proper subset, you need to add 1 first to get the number of improper, or regular subsets, not improper, regular. Here's the trickiest problem. This one, the way it's set up is only in the practice problems. It is not in the graded homework problems. And I'm not sure why they included it, because they don't really go into it in the textbook. But it's not too bad of a problem, and you can solve it by doing this sort of idea that I'm showing you here. You can also solve a problem like this by using a calculator, as I'll talk about in a little bit. So you have 5 different types of flowers, or 5 flowers. You want to choose 3 of them for a display. The order doesn't matter. How many unique displays can you have? And rather than naming flowers and saying, oh, I have marigolds and petunias and roses and tulips, I'm just going to call them A, B, C, D, E. So what I can do here is I can just list all of the possibilities. So I can have these different groups of 3 or subsets of 3 from my original 5 flowers. I can have ABC or ABD or ABE. I can have ACD or ACE. I have ACE there twice. I can have ACD or ACB or ACE. Let me fix this. Okay, let me correct myself here. Let me re-show the PowerPoint. All right, let's try that again. We can have ABC or ABD or ABE. We can then have ACD or ACE. And then we could have ADE. Those are all possibilities where we have A as one of our flowers. Now, other possibilities, if we don't have A, and if we're leaving A out, we could have BCD or BCE or BDE. And so if we're leaving both A and B out, then we have 3 possibilities left. We can have CDE. And so when I count all of these up, there are 10 different displays possible. This is a special problem that's called, the combination problem. And in math notation, we usually write it as 5 as a subscript, and then a big capital C, and then 3 as a subscript. And we read this as 5, choose 3. We do this when we're picking a certain number, like here we're choosing 3 out of 5, and the order doesn't matter. Many calculators have this notation built in. So if you have a TI-83 or a TI-84 calculator, for example, it has that built in. You can also simply, in this class, go to Google for it, and you can type in 5 choose 3 in Google, like I did here on this screenshot. And so if you type in 5 choose 3, notice there's tons of results, but it will show you the calculator at the start, and it will tell you what the answer is. It will also give you helpful hints on how to do it. There is a formula here. I'm going to introduce the formula to you, and you're not expected to know it. But the formula is this. It is this idea of NCR, where N is the number we're selecting from. Like here in our example, N was 5. And then we were choosing 3 of the 5. So N is the number we're working with, and then R is the number we're choosing from that number. The formula is N factorial divided by the quantity N minus R factorial times R factorial. And factorial is a really cool mathematical operation. A number's factorial means you take that number, it only works with natural numbers, and you multiply it by all the smaller natural numbers down to 1. So 4 factorial will be 4 times 3 times 2 times 1, which is 24. 3 factorial is 3 times 2 times 1, which is 6. 5 factorial will be 5 times 4 times 3 times 2 times 1, which is 120, I believe, and so on. Factorials get really big really quickly. There are shortcuts that we aren't going to worry about in this class for dealing with big ones because it's outside of what we need to worry about. But factorials are cool. So yeah. Now, here is a type of problem that is going to show up in the homework, the graded homework, and it's when you don't need factorials or calculators to solve. You have 5 textbooks. You have a history book, a math book, a science book, a geography book, and an art book, and I've given those all letters. How many ways could you arrange them if you want to put them on a shelf, for example, and you're using all the books? So here, your order does matter. So having the history book first is a different order than having the math book first. So in this case, order does matter. So you could make a list. Your list is certainly doable, but you would have lots of entries in the list. It would be really easy to miss something. But you can just think about it. You have 5 choices for your first book, right? The first book you choose could be your history book, your math book, your science book, your geography book, or your art book. Whatever one you choose, it doesn't matter which one you choose, but then you know for your next choice, you only have 4 choices left because maybe I chose my art book first. So I have 4 choices left for the next book. Then I just have 3 choices left for the next book. Then I have 2 choices left for the next book. And then finally, I have just 1 choice left. So the fundamental counting principle applies here. 5 choices times 4 times 3 times 2 times 1, that's 120 choices. You might notice that that number changed from a couple of seconds ago because I realized that I multiplied wrong. But we can see what I did here. 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, and of course, any number times 1 is that number, so 120. And 120 is actually, interesting enough, the same as 5 factorial. Factorials are important in problems where you're doing different types of choice, which we also kind of confusingly call counting problems. So you're going to have a similar problem to this on the graded homework. It'll be a little simpler because instead of having 5 choices, 5 things to work about, you're just having 4 things. So it's same process, just it's going to be a smaller number. Finally, just some content I want to talk about. We might come back to this, but it's sort of mentioned in this section. There are different types or sets of numbers that you do need to be aware of as elementary teachers. So the first type of numbers that I mentioned in one of the earlier videos are natural numbers. These are also called counting numbers. And this set has a special letter for it. It's the letter N for natural. And this is the set of numbers that starts with the number 1 and it keeps increasing. It goes on forever. So we call this an infinite set in that it never ends. So its cardinality, the n of n, is infinity, like it never ends. That's true for all of these. W isn't a standard letter for it, but it's most commonly used. These are the whole numbers. The whole numbers are the natural numbers plus 0. And the difference here is they're called natural numbers because think about for little kids, when we teach little kids how to count, we usually don't teach them to count 0, 1, 2, 3, 4. We teach them to count 1, 2, 3, 4. I will say that if you are an international student, if you're not from the US originally, and you've taken math elsewhere in another country, some countries don't differentiate between these two. They believe that 0 is a natural number. It's not set in stone elsewhere, but in the US, the vast majority of the time, we consider it like this. And then integers. Integers are basically the whole numbers and their opposites. So the integers go to negative infinity, and then they go, for example, to -3, -2, -1, 0, 1, 2, 3, and then they keep going to positive infinity. Ignore that line there. That's just an those are artifacts from PowerPoint. And then finally, the rational numbers are numbers that could be represented as a fraction, even if they aren't. So any number they could be represented as some integer over some other integer, as long as the bottom integer isn't 0. So 1/3 is a rational number, but so is 4 over 1. So is 0 over -7. So is 1,000 over 50. Now, many of these could be simplified, right? 4 over 1 simplifies to 4. 0 divided by -7 is 0, and so on. It doesn't matter. It matters that they could be represented as a fraction. So, for example, many numbers are in more than one of these sets. So we look at the universal set of all numbers. We have the smallest set as being the natural numbers, and then slightly bigger, just one more, are the whole numbers, because the whole numbers are the natural numbers plus 0. And then bigger still are the integers, and then bigger still are the rational numbers, which include the integers inside of them. So we can say, for example, that the natural numbers are a subset of the whole numbers. They're also a subset of the integers. They're also a subset of the rationals. There are other types of numbers as well. All of these are called, for example, real numbers. You might recall if you took Algebra 2 in high school, there are also imaginary numbers. Those are not real. We don't worry about those in elementary school. There are also irrational numbers. A pi, for example, is an irrational number. We'll talk about those briefly, maybe later in the course. But these will be the main things. These are the most common numbers in elementary math, particularly the natural numbers, the whole numbers, and the rational numbers. Integers often don't come around until the upper elementary, even the middle school grades. But we will use these throughout the book, so I want you to be familiar with them. So a lot of information there. I do believe this will help you on the homework. I'm going to do one more video about the homework, about the problem that I created, because it's something I think you should know. And then also, this is the homework from section 2. I'll do more videos about section 3, which is a little trickier in some cases and has some more homework problems associated with it. I do hope this helps. Please let me know if it helps or not, if you're in the course and not just finding this randomly on YouTube. So good luck, and keep moving forward. I want to point out that this information is, for most students, it is overwhelmingly new in this course. It is not a huge part of the course as a whole. So as I mentioned in one of the introductory videos, you can do poorly on this module, in this chapter especially, You can struggle with it, and it's not going to harm you in the rest of the course. Math does build on itself, but this class is a little different because we are really going from topic to topic to topic. And so if you don't have a firm grasp on set theory, that is not going to hurt you for the rest of the course. So do your best, but do not over stress about this material. Thanks.